In example 46, we're going to solve a couple systems of equations, and we'll see how this approach using matrix inverses can actually be quite a time saver in certain situations. So I'm going to start out just by writing the matrix equation for each of these systems. And in part B, so one thing we can notice right away is that these both have the same coefficient matrix. And in fact, it is the same as the coefficient matrix from the last example. So we do know the inverse of this matrix. And so I'm just going to jot that down before we proceed. And again, we'll call this our matrix A. And so we know that A inverse is this matrix here. Now, the advantage that we get from solving certain systems of equations using a matrix inverse is precisely when we might be presented with perhaps a few different systems of equations that have the same matrix inverse. We know that it's a bit of a process to go through finding the inverse of a matrix using Gauss-Jordan elimination. Basically the same process that you have to go through when you're solving a system using our matrix methods that we learned before. So the advantage if I have a couple of systems with the same coefficient matrix is that I only have to go through that process once to find the inverse. In this case, we've already got that inverse. So we know that our solution is going to be given by right multiplying each side by the matrix inverse, which yields the matrix equation of our unknown X matrix equal to A inverse times B. So in part A, it'll look like this. And we can find this product. I'm going to find the item in row 1 first. I'm going to multiply the first row of this A inverse by our column matrix here. So we've got 3 plus negative 3 plus negative 2. Second row, got 3 plus negative 6 plus negative 2. And third row, negative 3 plus 3 plus 4. And this gives us negative 2, negative 5, and positive 4. And so what this means, since this is our X matrix, this means that x1 is negative 2, x2 is negative 5, and x3 is equal to 4. In part B, we're going to go about this the same way. We're starting here with our matrix equation. We know that we'll get the solution by right multiplying each side by the inverse of that coefficient matrix. And that will give us the following. So I've got my A inverse matrix here. multiplied by our constant column matrix. All right, in row 1, negative 5 plus 1 plus 4. In row 2, negative 5 plus 2 plus 4. And in row 3, 5 plus negative 1 plus negative 8, or 0, 1, negative 4. And so this means that our solution for the system of equations in part B is x1 equals 0, x2 equals 1, x3 equals 4. Even if we hadn't already had the inverse of this matrix from a previous example, we would only have had to go through the process to find that inverse once, right? And then we would be able to use it again, use it for both of these systems because the coefficient matrices were the same.